Now, what if in looking for our permutations on a given multiset where the identical elements, let's say b sub 1, b sub 2 until b sub k, have infinitely many duplicates, what would be the final form that we need in order for us to determine the number of ways in arranging r or getting r permutations for a specific r? Now, let's not forget that this is still an example of exponential generating function because we're talking about r permutations, not selections. So this might be different from the previously discussed formula as well for the for selection of r members or r objects in a multiset. Okay, because that includes ordinary generating function. This time we'll talk about exponential generating function. To do this, of course, we just need to identify the correct coefficient for the numerical coefficient x to the power of r over r factorial. So that is actually the value here, whatever would be that a sub r, that determines the number of arrangements here. Hence, we're going to generalize a sub r for this given situation. To do that, let's try to come up with equivalent exponential generating functions for each of the given terms here in the multiset. So for b sub 1, we have here 1 plus x plus, sorry, it should be exponential. So you have x divided by 1 factorial plus x squared over 2 factorial plus x plus until you reach x to the power of r, okay, over so on and so forth, right? So let's just simply have that over r factorial. But not to confuse with the r we're looking for here, let's use another variable here, or just simply remove that because we know that to extend so on and so forth. So for b sub 2, or the second element with infinitely many duplicates, same, will go 1 plus x plus over, sorry, 1 factorial, I forgot that, x squared. Let me rewrite this one, including this one here. Okay, so it's actually b sub 1 here. So for b sub 2 over 1 factorial, 2 factorial here, plus so on and so forth. Until you reach here for b sub k, still 1 plus x over 1 factorial plus x squared over 2 factorial plus so on and so forth. Okay, so looking into this, since there are k different distinct objects with infinitely many duplicates, that would mean there are also k pieces of this being multiplied. So in one exponentiation, we can write this in this form: 1 plus x over 1 factorial plus x squared over 2 factorial plus so on and so forth, power of k. That's the condensed way of writing the product of k pieces of the same exponential generating function. Now, take note, we know this to have already a specific equivalent expression. Specifically, we can actually have here, using exponentiation, that's actually e to the power of x. And since e to the power of x is raised to k, okay, this entire form, which is again e to the power of x, or what we know to be the summation of x to the power of r over r factorial, as we have here, r starts from 0 to positive infinity. In this form, it's just like that. We're using this form because we can apply here the power law. Since we have the power here, this is actually equal to e to the power of kx. And we also have another identity for this. That is the reason why we discussed previous identities and their derivation, because this is equal to the summation of k x power of r over r factorial. Then we have here as r starts from 0 to positive infinity. Now we're getting closer because what we want is this form here. What you want is to have this form, and then whatever will be the remaining result here stands for our a sub r, the generalized formula for this type of situation. Simplifying this, we actually have here the summation of k to the power of r, x to the power of r over r factorial, as r starts from 0 to positive infinity. Then, we already have this notation now. So what is this? That's actually our a sub r. In short, the formula for a sub r in getting r permutations for the given multiset where there are infinitely many duplicates for the distinct objects there, this is actually equal to k to the power of r. Now, say for example, if you have these situations and you're trying to find out the number of 5 permutations in a given multiset, So you simply substitute here 5 to get the value, and your K is again the number of distinct objects presented in the given multiset. So this is the formula, and we might be able to use that in a specific situation soon. Thank you very much for watching.